The Boötes Void is identified as a broad region of unusually low galaxy density, in the direction of the constellation Boötes revealed through three-dimensional mapping of galaxies, rather than through any visible darkness on the sky. The stars of Boötes are nearby members of the Milky Way's foreground. The void lies far beyond them at distances of hundreds of millions of light-years, where the night sky's familiar constellations become mere directions on a sphere. In modern surveys, each distant galaxy is recorded with a position on the sky and a distance estimate derived from the stretching of its light by cosmic expansion. That stretching is measured as redshift, a shift of spectral features to longer wavelengths. When many galaxies are plotted in 3 dimensions using their sky coordinates and redshifts, they do not fill space evenly. They gather along filaments and broad sheets with large cavities between them. The Boötes Void stands out as one of the most prominent cavities in the nearby universe, because its interior contains far fewer galaxies than an average region of similar volume. Its scale is expressed in the language of large-scale structure, a diameter on the order of hundreds of millions of light-years, with a centre at a distance, also of hundreds of millions of light-years from Earth. The precise numbers vary with the survey used and with the definition of the void boundary, because a void is not a hard-edged object. Its boundary is drawn where galaxy density rises from very low to less low, and that transition is gradual and irregular. In practice, observers define a threshold relative to the cosmic mean density of the tracer galaxies in the survey, then identify the connected region that falls below that threshold. Under one definition, the void core is smaller and deeper. Under another definition, the void includes surrounding under dense extensions, making it larger and less uniform. Despite these definitional choices, the same essential feature persists across surveys in that direction, and at those distances galaxies are sparse compared to neighbouring regions. The discovery and confirmation of the Boötes Void depend on mapping strategies that balance depth area and completeness. Early surveys that first highlighted the region relied on optical imaging to identify galaxies, and then on spectroscopy to measure redshifts. The key evidence is statistical. When a survey is complete above a chosen brightness limit within a chosen distance range, the number of galaxies within a large volume can be compared to the number expected based on the survey's average density. In the Boötes region, that number is unusually low. This deficit is not limited to one thin slice of sky, or one narrow distance interval. It appears as a contiguous underdensity across a substantial volume. Later surveys with improved detectors, wider coverage, and better calibration have refined the shape and the internal inventory, but they have not erased the basic feature. The void remains a clear example of how the cosmic web contains not only concentrations of matter, but also vast regions where matter as traced by luminous galaxies is thin. Locating the void in 3 dimensions requires careful attention to what is being measured. A galaxy's redshift includes the contribution from cosmic expansion, and a smaller contribution from its motion relative to the general expansion, called peculiar velocity. Peculiar velocities can shift the inferred distance slightly along the line of sight, creating distortions in redshift space maps. In dense regions, random motions in clusters can smear galaxy positions into elongated features. In under-dense regions, coherent outflows can alter apparent shapes. Because the Boötes Void is so large, the overall identification of a major underdensity is robust to these effects, but the fine structure of the boundary and the depth profile can be influenced. Analysts often smooth the galaxy distribution on large scales to reduce sensitivity to small distortions, then identify the underdense basin. The resulting void is therefore a feature defined on large scales rather than a sharp contour. The sky location also matters because surveys have masks and limits. Bright foreground stars, regions of high Milky Way dust, and gaps in observing coverage can produce artificial underdensities in a catalogue. The Boötes Void's persistence across multiple independent surveys reduces the likelihood that it is merely an artifact of masking. But any careful description still treats the void as an observational construct derived from data with known limitations. The void is easiest to detect in bright galaxy samples because bright galaxies are most strongly clustered and most absent in under-dense regions. This can make the void appear more dramatic in shallow surveys that detect primarily bright galaxies. As surveys go deeper, fainter galaxies appear, including low-mass and low-surface brightness systems that can inhabit low-density environments. The void can then look less empty in terms of raw counts. This does not necessarily mean the void is less underdense in mass. It means the tracer population has changed. A consistent comparison requires defining the void using the same tracer class and the same selection in both observation and simulation. Within that context, the phrase that the void revealed something never expected must be approached as a question about which quantity is being compared and at what threshold. A surprise can arise if the void's measured size seems unusually large for the survey volume, or if the interior appears too empty even after accounting for tracer selection. It can arise if galaxies inside the void show properties that appear inconsistent with the usual relationship between environment and star formation. It can arise if gas absorption measurements suggest an unexpectedly dense or enriched intergalactic medium in the deepest interior. It can arise if dynamical signatures such as inferred outflow velocities imply a mass deficit deeper than models allow. But before any of these possibilities can be evaluated, the void must be placed precisely in observational space, where it sits, how large it is under a chosen definition, and what distance interval is being discussed. The Boötes Void is therefore best introduced not as a mysterious whole, but as a named extreme in the distribution of underdense regions in the cosmic web. It is a landmark defined by a deficit of galaxies over a vast volume. That deficit is measured in redshift surveys conditioned on selection limits and framed by the surrounding higher density walls and filaments. With the void located in this disciplined way, the next step is to examine how emptiness is measured in practice, because the meaning of any claimed revelation depends on the details of completeness. Surface brightness limits and the conversion from observed light to inferred three-dimensional structure. Measuring emptiness in a region like the Boötes Void begins with measuring what is present, and then proving that what appears absent is not an artifact of how the measurements are made. The fundamental data product is a galaxy catalogue, a list of objects with sky positions, brightnesses and distances. The distance information usually comes from redshift extracted from a spectrum. A spectrum spreads a galaxy's light into its component wavelengths, revealing patterns of absorption and emission features. Those features shift in wavelength when the galaxy is moving away as space expands. The redshift is a precise measurement, but translating it into a three-dimensional position requires a chain of assumptions and corrections. The first assumption is that most of the redshift is due to cosmic expansion rather than local motion. The second is that the survey has measured redshifts for a representative set of galaxies above its detection threshold. The third is that the detection threshold itself is uniform enough that a region does not look empty simply because it is observed less deeply. Brightness limits are the most obvious selection effect. An imaging survey detects objects down to some apparent magnitude set by exposure time, telescope aperture, sky brightness, and detector performance. A spectroscopic survey then chooses targets from the imaging list, but it cannot measure spectra for all targets. It selects by brightness, by colour, by size, or by other criteria that optimize the science goals and the efficiency of the instrument. This creates a spectroscopic selection function layered on top of the imaging selection. In void work, the safest approach is to define a volume-limited sample. This means choosing a maximum distance and a minimum intrinsic brightness, such that any galaxy brighter than the intrinsic limit would be detectable and would have been targeted across the entire survey footprint. Within that volume, the catalogue can be treated as complete for that class of galaxies, and density estimates can be made without large correction factors. The trade-off is that the sample excludes faint galaxies. In a void where galaxies may be predominantly faint, this exclusion can make the void appear more empty than it is in raw number, though the emptiness relative to the average for the same sample remains meaningful. Surface brightness limits add a subtler but often more important layer. A galaxy's detectability is not determined only by its total light, but by how that light is distributed. If the light is spread thinly, the galaxy can blend into the background and fail detection, even if its total brightness is moderate. Low surface brightness galaxies are common in low-density environments, at least in relative terms, because they can have diffuse stellar distributions and low star formation rates. In the Boötes region, if a population of such galaxies exists, an optical survey optimized for compact high-contrast sources could miss them preferentially. This introduces a bias that specifically affects void interiors. Modern pipelines attempt to correct for this, but the correction is incomplete because the missed population is by definition hard to quantify. A practical way to assess this effect is to compare optical catalogues to neutral hydrogen surveys. Neutral hydrogen emission at radio wavelengths can reveal gas-rich galaxies that are optically faint or diffuse. If radio surveys find galaxies in regions where optical surveys see little, the perceived emptiness changes. However, radio surveys also have selection effects favouring gas-rich systems and missing gas-poor dwarfs. Therefore, emptiness depends on the tracer. Distance assignment introduces another source of apparent structure. Redshift is affected by peculiar velocity, the motion of a galaxy relative to the smooth expansion. Peculiar velocities can shift the inferred position along the line of sight by an amount comparable to several million light-years or more, depending on the velocity and the distance. In dense regions, random motions within clusters can smear galaxies into elongated structures that appear to point toward or away from a void boundary. In under-dense regions, coherent outflows can slightly stretch the void along the line of sight. These redshift space distortions alter the apparent density field and can change which galaxies are classified as inside the void. To address this, analysts either work consistently in redshift space, comparing observations to redshift space simulations, or attempt to reconstruct real space positions using velocity models. For a large void, consistent redshift space treatment is often sufficient, but it must be stated explicitly. Otherwise, a comparison to real space model expectations can be unfair. Survey geometry is another critical factor. Surveys cover finite areas, avoid bright stars, and have gaps. These features are encoded in a mask that describes where data exist and where they do not. If a void-finding algorithm treats unobserved regions as empty, it can create false voids or enlarge real ones. Proper analysis uses the mask and often constructs a random catalogue, a set of points distributed according to the same angular selection and radial selection as the survey. By comparing the observed galaxy distribution to the random distribution, one can estimate densities corrected for geometry. In a region like Boötes, where the void spans a large angle, edge effects can be significant if the survey footprint is irregular across that area. Cross-checking the void in independent surveys with different footprints provides confidence that the void is not driven by a particular mask. Foreground extinction from Milky Way dust is another source of bias. Dust dims background galaxies, reducing their apparent brightness and making some fall below the detection threshold. Extinction varies across the sky. Surveys correct for it using dust maps, but residual errors can remain. In a shallow survey, a slightly dustier patch can produce a noticeable deficit of galaxies. For a deep void like Boötes, extinction is unlikely to explain the full deficit, but it can shape the detailed boundary, and affect the census of faint galaxies near the threshold. A careful measurement of emptiness therefore includes extinction corrections, and ideally checks whether the void's location coincides with unusual dust structures. Once the catalogue is assembled with these factors accounted for, density estimation within the void is still non-trivial because of sparse sampling. In a dense region, one can measure density on small scales because many galaxies are available. In a void, density estimates must use larger smoothing scales to reduce noise. A common method is to measure distances to nearest neighbour galaxies, or to count galaxies within a fixed radius. In a void, these measures can be dominated by a few objects, and can vary widely depending on whether a faint internal filament is present. Therefore, claims of sharp internal features or unexpectedly deep cores must specify the smoothing scale, and must show that the feature is not consistent with shot noise, the random variation expected when counts are small. A crucial practice is to define a baseline expectation that matches the measurement. If emptiness is measured for galaxies brighter than a given intrinsic brightness within a given volume, the model comparison must use the same brightness cut and volume. If the void is identified in a particular survey with a particular mask, the model comparison must include that mask. If the measurement is done in redshift space, the comparison must be in redshift space. When these matchings are not made apparent, contradictions can appear because the model is being asked to predict an observation that is not defined consistently. In this discipline view, emptiness is an operational quantity, not an absolute one. The Boötes void can be empty of bright galaxies, while still containing faint dwarfs, diffuse gas and dark matter halos. It can be empty in optical light, but less empty in gas. It can be empty in galaxy counts, but only moderately underdense in mass. Each of these is a different measurement. The phrase that the void revealed something never expected becomes meaningful only when attached to one of these measurements. The next inward step is therefore to set emptiness against its outer context by describing the surrounding walls and filaments that define the void boundary, because the contrast between boundary and interior is the empirical signature that makes the void stand out in the first place. The Boötes void is outlined by what lies around it, and the surrounding cosmic web provides both the definition of the void's boundary and the physical context that shapes its interior. In three-dimensional galaxy maps, the regions bordering the void show the familiar pattern of higher density structure filaments that run for tens of millions of light-years, broad sheets where galaxies form a wall-like distribution, and knots where groups and clusters collect. These features are not arranged as a neat shell. They form an irregular enclosure that traces the underlying mass distribution. The void boundary is therefore not a surface, but a zone where density rises, and that rise is marked by the return of filaments and walls. In practice, the boundary is identified by measuring galaxy density as a function of position, and finding the contours where the density crosses a chosen threshold. Those contours wrap around the underdense basin that defines the void. The cosmic web around Boötes is what makes the void visible in data, because the contrast between the sparse interior and the richer exterior is what gives the void its identity. Filaments are elongated structures where galaxies and galaxy groups align, reflecting the presence of dark matter strands that channel matter. A galaxy in a filament often has a preferred orientation and a set of nearby neighbours along the filament axis. Walls are broader sheets where the web structure is more planar. In many surveys, walls appear as broad surfaces of enhanced galaxy density separating neighbouring voids. The region around Boötes shows both types of features. The void sits amid a complex environment in which matter is not evenly distributed. This complexity matters because a void is not an isolated bubble. It is part of a connected network. A boundary filament can connect to another filament far away, and the void can connect through lower density passages to neighbouring underdense regions. These connections shape both the geometry and the evolution of the void. The boundary zone is where matter that would have occupied the void interior is relatively concentrated. In gravitational terms, an underdense region experiences less inward pull, so the outward expansion is less slowed. Over time, matter flows outward from the underdense region towards surrounding denser regions. This flow helps build up the boundary structures. As a result, the boundary can show an enhancement in density relative to the mean, sometimes forming a ridge around the void. Whether that ridge fully compensates the mass deficit inside depends on the larger environment. In some cases, the ridge balances the deficit, producing a compensated void. In other cases, the void is embedded in a broader underdensity and is less compensated. For Boötes, the existence of surrounding walls and filaments implies local compensation in the sense that mass has gathered around the edges, but the degree of compensation on larger scales is an empirical question. The boundary region is also where observational traces are most abundant, making it the best sample part of the void system. This has two consequences. First, the boundary is measured more precisely than the interior, because there are more galaxies to trace it. Second, any mismatch between model predictions and observations often arises at the boundary, because that is where profiles are compared. For example, if the model predicts a certain steepness of the density rise, and the observed rise appears sharper, the discrepancy is driven by boundary measurements. However, boundary sharpness can be affected by selection effects. If the interior contains faint galaxies below the survey limit, the transition from boundary to interior appears sharper than it truly is in mass or in a deeper tracer population. Therefore, the apparent contrast between boundary and interior depends on survey depth, and the boundary must be interpreted with that in mind. The boundary is also where galaxy environments change rapidly. Outside the void, galaxies are more likely to be in groups to experience interactions and to be influenced by the tidal field of neighbouring structures. Inside the void, galaxies become more isolated. The boundary zone is therefore not only a geometric feature, but an environmental gradient. Galaxies near the boundary can have properties intermediate between field and void, and they may still be influenced by filamentary gas inflows. This matters when interior galaxies are catalogued because some galaxies classified as inside the void may actually lie in thin filaments that intrude inward from the boundary. Such galaxies can have higher local density than the void average, and can resemble filament galaxies more than true void core galaxies. If these are not separated, the interior population can appear less isolated than it is. Conversely, if one defines the void too conservatively and excludes boundary intrusions, the void appears deeper and more empty. This definitional sensitivity is a major reason void claims can vary. Beyond galaxies, the boundary structures are also expected to host warmer and denser gas than the interior. Gas in filaments is compressed and can be heated by gravitational collapse and shocks. This produces a warm to hot intergalactic medium that can be traced through specific absorption lines and in the densest regions through faint X-ray emission. The boundary therefore marks not only a rise in galaxy density, but also a change in gas phase. If one searches for gas absorption along sightlines that pass near the boundary, and compares it to sightlines through the core, one expects stronger and more frequent absorption near the boundary. This provides an independent way to trace the void's density gradient in baryons. For Boötes, such tests are limited by the availability of bright background sources, but the physical expectation is clear. The boundary region also shapes dynamics. Galaxies near the void experience an outward peculiar velocity relative to the void center, while galaxies in surrounding overdensities experience infall toward those overdensities. The boundary is where these competing influences can meet. The velocity field can be anisotropic, stronger in directions where the void is deeper and weaker toward massive nearby structures. In redshift space, this can create asymmetries in the apparent void shape. If a survey slice passes through the boundary in a direction aligned with the line of sight, distortions can make the boundary appear shifted. Therefore, a proper understanding of the boundary involves not only static density but also motion. In narratives that say the Boötes Void revealed something never expected, the boundary is often the silent premise. The void appears dramatic because the surrounding regions appear normal or even crowded by comparison. The boundary defines what normal looks like locally. A surprising interior claim must therefore be judged relative to this boundary context. If the boundary structures are unusually strong or unusually arranged, the void may appear more exceptional. If the boundary is incomplete due to survey coverage, the void may appear larger. If the boundary is traced only by bright galaxies, the interior may appear emptier. Thus, the boundary is not merely an outer decoration, it is the measurement anchor. At this stage, the void's outer structure is established as an irregular enclosure of filaments and walls that both defines the void and influences how it is sampled. The next inward step is to move from this present-day boundary to the void's origin, describing how such a large underdense basin arises from early density variations, and how it grows over time into a feature like Boötes, because the plausibility of any unexpected revelation depends on whether the void's size and depth can be produced naturally by gravitational evolution in the standard framework. A void as large as Boötes is the late-time outcome of small early differences in density, amplified and reshaped by gravity in an expanding universe. In the early universe, matter is nearly uniform, but it contains tiny fluctuations, with some regions slightly denser than average, and others slightly less dense. These fluctuations are measured indirectly through the cosmic microwave background, the relic radiation from the early hot phase of the universe, which shows temperature and polarization variations corresponding to early density ripples. The fluctuations are small, but they are present on many length scales. Gravity acts on these fluctuations continuously. Where density is slightly higher, matter pulls in more matter and grows denser. Where density is slightly lower, it pulls in less matter and becomes comparatively emptier as the surrounding denser regions grow. A void forms when an underdense region expands relative to its surroundings, not by creating a physical cavity in a pre-existing medium, but by becoming a region that lags in structure formation and loses matter to neighbouring regions over cosmic time. The term expands here refers to the behaviour of matter within the cosmic expansion. All distances between distant galaxies increase over time due to the expansion of space. However, gravity can slow this expansion locally in overdense regions. In an underdense region, there is less gravity to slow the expansion, so the local recession of matter is closer to the unimpeded background expansion. Over time, this difference leads to a relative evacuation. Matter moves away from the underdense centre towards surrounding denser regions, building up filaments and walls and deepening the underdensity. In simulations, this process produces a characteristic void profile, a low-density core and a boundary region where matter becomes more concentrated. The boundary is not a shell that forms suddenly. It is the accumulation of displaced matter along the cosmic web. The scale of a void depends on the scale of the initial underdensity and on how multiple underdense regions merge. The cosmic density field contains many basins of underdensity. As the universe evolves, some basins become separated by thin walls. If those walls weaken and the density contrast between basins remains low, the basins can merge into a larger void. This merging is not a collision, but a gradual topological change in the density field as matter flows outward. The merged void is larger and can have internal substructure, including residual ridges and faint filaments that mark the former boundaries. This is important for understanding a large void like Boötes, because it suggests that its size can arise not only from a single large primordial underdensity, but also from the coalescence of multiple smaller voids. Large voids are therefore natural in a hierarchical structure formation picture where both overdense and underdense structures evolve and merge In standard cosmology, the statistical properties of the initial density field are described by a power spectrum which specifies how much fluctuation power exists on different scales. The power spectrum is constrained by early universe observations. Given these constraints, simulations generate initial conditions and evolve them forward under gravity. In such simulations, voids appear in abundance. Most are smaller than Boötes, but some can reach comparable scales, particularly when defined by galaxy traces rather than by mass. The rarity of very large voids is expected because large coherent underdensities are less common in the initial field. Yet in a universe with enormous volume, rare structures appear. The presence of one prominent void in the nearby universe is not inherently inconsistent. The question becomes whether its properties place it in an extreme tail that is statistically incompatible with the surveyed volume and the model parameters. The evolution of voids is influenced by the changing expansion rate of the universe. In the earlier universe, when matter dominates the energy density structure, growth is faster, and density contrasts evolve more rapidly. Under dense regions expand relative to average and deepen in contrast. At later times, dark energy becomes more important and accelerates the overall expansion, slowing the growth of structure. This does not stop void evolution, but it reduces the rate at which density contrasts change. For a nearby void like Boötes, most of its major growth occurs over billions of years and is already largely complete in the sense that the cosmic web's large-scale pattern changes slowly at late times. The void's present-day depth and size reflect this full history of growth under an evolving background. A key point is that void formation is tied to mass rather than to light. The mass field evolves under gravity and sets the void. Galaxies form later within dark matter halos that themselves form within the mass field. Because halo formation is delayed in underdense regions, and because galaxy formation efficiency can be suppressed in low-mass halos, the galaxy distribution can exaggerate voids. This is why a void can appear very empty of bright galaxies, even if the mass under density is more moderate. In formation terms, the mass void is the primary object. The galaxy void is a tracer-dependent representation. Therefore, when a void is said to reveal something unexpected, one must ask whether the unexpected feature lies in the mass field or in the tracer behavior. If it lies in tracer behavior, the explanation may lie in galaxy formation physics or in survey limits rather than in cosmology. The Boötes Void's boundaries are consistent with the formation picture. The surrounding filaments and walls indicate where matter has accumulated. The interior's scarcity of massive galaxies indicates a suppression of massive halo formation. The presence of some galaxies indicates that the underdensity is not complete, and that smaller halos still form. All of this aligns qualitatively with simulations. Potential tension would require quantitative mismatch, such as a void that is both extremely large and extremely deep in mass beyond what the initial fluctuation statistics allow. This would be a claim about the initial conditions or the growth rate, not about galaxy formation. Testing it requires mass-sensitive probes and careful statistical modeling. Void merging and environmental embedding also offer conventional ways to interpret extreme appearance. If Boötes is part of a larger underdense region, or connected to adjacent voids through low-density channels, its apparent size can be large under certain definitions. If the void is measured using bright galaxies, the interior can appear particularly empty. If the boundary structures are strong in the local environment, contrast can appear sharper. None of these require new physics. They require careful definition and comparison. At this stage, the origin of Boötes is grounded in the standard mechanism small early underdensities expand, relative to their surroundings, evacuate matter toward edges, and can merge to form very large cavities in the cosmic web. This origin makes the void itself plausible, and sets expectations for what should remain inside a diluted dark matter network, diffuse gas, and a small population of galaxies. The next inward step is to state those interior expectations, more explicitly establishing the baseline model predictions for what should be present inside such a large void, before turning to what is actually observed there and what might be labelled as unexpected. With the void's formation grounded in standard structure growth, the next inward region is the baseline expectation for what remains inside a very large void once it has evolved to the present epoch. The baseline is not a picture of nothingness. It is a picture of reduced density across multiple components, dark matter, ordinary gas, and the galaxies that form in some fraction of dark matter halos. Models predict these components in linked ways. Dark matter sets the gravitational scaffolding. Gas follows the scaffolding but is smoothed by pressure and heated and ionized by radiation. Galaxies form only where gas can cool and condense in halos, and their visibility depends on star formation and on the survey's sensitivity. In a void like Boötes, each link in this chain tilts towards scarcity, so the void appears as a profound deficit of luminous galaxies, even when a substantial amount of matter remains in diffuse and dark forms. The dark matter expectation begins with halos, the gravitationally bound concentrations where galaxies can form. In under-dense regions, halo growth is slower, and the abundance of high-mass halos is strongly suppressed. This means that within the void interior one expects very few halos massive enough to host bright massive galaxies. Instead, one expects a population dominated by low-mass halos. These halos can be isolated and separated by large distances, and they can be embedded in weak internal filaments that are the remnants of the initial fluctuation field. The internal filaments are thinner and lower density than external filaments, but they are not absent. They provide a weak connectivity that can organize the placement of the halos that do exist. In simulations, the void interior often looks like a faint web with a small number of nodes and strands, where density is slightly higher than the surrounding void medium. This is the mass-level baseline, a diluted low-contrast network rather than a smooth uniform emptiness. The baryonic gas expectation is that most ordinary matter in the void remains in the intergalactic medium. In the present epoch, much of that medium is ionized by the ultraviolet background, a radiation field sustained by the cumulative light of galaxies and quasars. Ionized gas in low-density regions remains relatively warm, often in the range of tens of thousands of degrees, and it is too diffuse to emit strongly. In denser filaments, gas can be heated to higher temperatures by shocks. In the void interior, strong shocks are rarer, so a larger fraction of the gas may remain in the cooler photoionized phase. This affects detectability. The gas is primarily detectable through absorption lines in the spectra of background sources rather than through emission. The expected signature is weaker and less frequent hydrogen absorption than in filaments and fewer metal absorption lines, because void gas is expected to be less enriched by heavy elements. This expectation is statistical. A line of sight can still intersect an internal filament or a halo producing stronger absorption, but the average is lower. The galaxy expectation is built on the halo and gas expectations. In low-mass halos, gas accretion and cooling are more easily suppressed. One reason is that the gas surrounding the halo is warm and ionized, making it harder for the halo's gravity to capture it. Another reason is that cooling depends on density and on composition. In voids, gas densities are lower and metallicities can be lower, reducing cooling efficiency and making it harder for gas to form the cold molecular phase associated with star formation. As a result, many low-mass halos are expected to host either extremely faint galaxies or no luminous galaxy at all. This produces a mismatch between halo abundance and galaxy abundance, a mismatch that is strongest in low-density environments. It is an important baseline prediction because it explains why a void can appear emptier in light than in mass. For the galaxies that do form and are detectable, baseline models predict tendencies rather than strict types. Void galaxies are expected to be on average smaller in stellar mass, more likely to be disk-dominated and more gas-rich than similar mass galaxies in denser environments. They are expected to have fewer close neighbours and to experience fewer strong mergers, which reduces the probability of forming large ellipticals through repeated interactions. Their star formation histories are expected to be extended with star formation continuing to later times, because environmental quenching processes common in clusters such as stripping by hot intracluster gas are absent. Their metallicities are expected to be lower at fixed mass, because chemical enrichment proceeds through star formation and feedback, and is often accelerated by interactions and by gas recycling in dense environments. Inner void enrichment can be slower, and accretion of relatively pristine gas can be more significant. These trends are consistent with many observational studies across void environments, and they form the baseline against which any claim of unexpected behavior must be judged. The baseline also includes expectations for density profiles. In mass, a large void typically has a shallow core relative to smaller, more compact voids. This means that the fractional underdensity in mass is not necessarily extreme. In galaxies, especially bright galaxies, the underdensity can be very strong. The resulting galaxy density profile is often deeper than the mass profile. This difference is a feature of the model, not a contradiction. It reflects that luminous galaxies form preferentially in higher density regions and are rarer where halos are low mass. Therefore, when someone describes a void as almost empty, the baseline response is to ask empty of which traces. Empty of bright galaxies is expected. Empty of mass at the same level would be more unusual. Another baseline expectation concerns internal structure. Models predict that void interiors are not perfectly smooth. There can be subvoids, internal filaments, and modest clusters of low-mass halos. The presence of a few galaxies aligned along a faint filament inside Boötes would therefore not be unexpected. It would be a typical manifestation of internal substructure. What would be unexpected is a dense cluster or a rich group deep inside the core, because that would imply a massive halo and a locally high density region inconsistent with a deep underdensity. Even then, boundary misclassification and definition issues must be ruled out. A final baseline element is dynamics. A void is expected to be associated with an outflow velocity field, with matter moving away from the center relative to average expansion. This outflow is linked to the void's mass deficit. In redshift space, this can produce characteristic distortions in galaxy distributions around the void. The baseline expectation is that these distortions measured statistically are consistent with standard gravity and with the void's inferred density profile. For a single void, uncertainties are large, but the qualitative baseline remains. Taken together, these baseline expectations provide a calm reference point. Inside a void like Boötes, one expects a diluted dark matter network, diffuse mostly ionized gas that is hard to detect in emission, a scarcity of massive halos and luminous galaxies, and a small population of mostly low-mass gas-rich disk-dominated galaxies with extended star formation. This is what the model expects. The phrase that the void revealed something never expected can only be meaningful if it points to a departure from this baseline, and if that departure survives careful consideration of selection and statistics. The next inward step is to move from baseline expectations to the observed interior galaxy census for Boötes, describing what has been catalogued there, how it is distributed, and where the boundary between expected variation and potential surprise actually lies. Moving inward from the baseline to the specific observations, the next region is the interior galaxy census, as it is actually constructed for the Boötes Void. This census is not a single permanent list, but a set of catalogued objects whose membership depends on survey depth, void definition, and the criteria used to decide whether a galaxy lies in the true interior rather than in a boundary filament that intrudes inward. Even with these dependencies, the core observational fact remains stable. The Boötes Void contains far fewer galaxies than a typical region of similar volume, yet it contains a non-zero population of galaxies with measurable properties. Understanding what is revealed requires attention to how these galaxies are found, how they are distributed, and how their properties compare to galaxies outside the void. The census begins with redshift surveys that provide three-dimensional positions. A galaxy is considered inside the void if its position falls within the void volume, as defined by a density threshold. This can be done by identifying the void boundary first, then selecting galaxies within it, or by selecting galaxies in an angular and redshift range associated with the void, and then measuring local densities to determine whether they sit in the underdense region. Because the void is irregular, the second approach can mix boundary and interior objects, unless local density measures are used. A common practice is to compute a galaxy's nearest neighbour distance, or the density within a fixed radius, and use that as a proxy for environment. In the Boötes region, interior galaxies tend to have large nearest neighbour distances compared to galaxies outside, reinforcing the sense of isolation. Yet some galaxies classified as interior can still have modest local structure if they lie along a faint internal filament or near a sub-void ridge. This is expected and is part of the void's internal texture. Historically, early surveys found a surprisingly small number of galaxies in the Boötes volume given its size. The dramatic impression of emptiness comes from the contrast between the huge volume and the sparse set of points that mark luminous galaxies. Over time, as surveys deepen, additional galaxies have been identified. Some are faint and would not have appeared in earlier catalogues. Some are low surface brightness systems that require careful detection. Some are gas-rich galaxies found through radio emission. Even as this inventory grows, the density remains low relative to surrounding space. The void does not fill in to become normal. It becomes better characterized. The first lesson of the census is that emptiness is not absolute. It is conditional on observational thresholds, and those thresholds shift with technology. The distribution of the interior galaxies is typically not uniform. Some are closer to the void boundary where the density gradient is less severe and where residual filaments can reach inward. Others are deeper nearer the inferred centre of the underdensity. When plotted, the deeper interior can show large regions with no galaxies above the survey's luminosity limit, while the outer interior may show a sparse sprinkling of galaxies and small associations. This gradient is consistent with the expected density profile. It also means that any claim about something never expected must specify whether it occurs in the deep core or nearer the boundary. A surprising galaxy near the boundary may be less surprising than the same galaxy in the core because boundary environments are more connected to the cosmic web and more likely to host higher mass halos. The types of galaxies catalogued inside Boötes often align with general void tendencies. Many are late-type disk galaxies rather than large ellipticals. Many show ongoing star formation at some level. Gas measurements, when available, often indicate substantial neutral hydrogen reservoirs relative to stellar content. Some show low surface brightness features. These properties are consistent with isolation and with reduced interaction rates. Yet the census also includes diversity. A void does not enforce one morphology. It shifts probabilities. Therefore, the presence of a relatively normal spiral galaxy inside the void is not in itself unexpected. The more meaningful questions involve frequencies and extremes. How many galaxies of a given mass are present? How clustered they are, and whether any appear inconsistent with the expected halo population. One possible route to surprise is the presence of apparently massive or luminous galaxies deep in the void. A massive galaxy implies a massive halo, and massive halos are rare in a deep underdense region. To evaluate such a case, the census must verify distance and environment. Distance errors can move a galaxy into or out of the void along the line of sight. boundary definition can misclassify a galaxy in an intruding filament as interior. Even if the galaxy is truly in the interior, a rare massive halo can exist as an outlier. The question then becomes statistical. Is the presence of such a galaxy consistent with the tail of the halo mass distribution expected in a void of that size and depth? A single example rarely overturns a model. It can motivate deeper study of the local density field and of the galaxy's companions and gas content. Another route to surprise is the presence of small galaxies with extremely low metallicity or unusually high gas fractions. Such galaxies can look primitive, suggesting a slow evolutionary history. This is compatible with void expectations, but the extremeness can matter. If a galaxy's metallicity is far lower than typical for its mass, it may suggest recent accretion of pristine gas or unusually inefficient star formation. Both can occur in isolation. Confirming such extremes requires careful spectroscopy and calibration, because metallicity indicators can shift systematically. If confirmed, the galaxy becomes a test case for models of chemical evolution and gas inflow in low-density environments. Again, this is more likely to challenge galaxy formation prescriptions than cosmology. The census also offers hints about internal substructure. If interior galaxies appear aligned along a faint line or sheet, it may indicate an internal filament. Models predict such features. The challenge is that with few points alignments can occur by chance. Demonstrating a filament requires either more galaxies detected with deeper surveys or independent traces such as absorption systems that indicate higher density gas along the same region. If a filament is confirmed, it does not reduce the void's significance. It refines the picture the void contains, a weak internal web. This can even explain why some interior galaxies appear less isolated than expected, because they reside on that weak web rather than in the deepest emptiness. A further complication is that the census is often built from heterogeneous datasets. Different surveys have different selection functions. Combining them can introduce biases because one survey may be deeper in one part of the sky, while another is deeper elsewhere. If the combined catalogue is used to infer density, the patchy depth can mimic structure. A careful census either uses a single uniform survey for density measurements, or applies completeness corrections that account for the varying depth. For Boötes, this is particularly important because the void spans a large area and has been studied by multiple overlapping surveys over time. In summary, the interior galaxy census confirms that Boötes is a genuine underdensity in luminous traces, while also showing that the void contains a sparse but non-trivial population of galaxies. The census is shaped by selection and definition, and its interpretation depends on separating boundary intrusions from core membership. Within the census, potential surprises are most plausibly found in extremes, unusually massive galaxies deep inside unusually primitive galaxies, or unexpectedly coherent internal structure. Each of these requires careful confirmation and statistical framing. The next inward step is to focus on the processes within these galaxies, beginning with star formation in isolation, because the visibility and perceived novelty of void galaxies depend strongly on how gas turns into stars when external influences are minimal. In the interior of a large void, a galaxy's star formation proceeds with fewer external disturbances, but it still depends on the same physical requirements as anywhere else. Cold, dense gas, the ability of that gas to cool and fragment, and a balance between collapse and feedback. The difference is that in a void, the surrounding environment supplies fewer strong triggers, such as major mergers, and fewer suppressors, such as stripping by hot gas in groups and clusters. This shifts star formation toward a regime where internal processes and slow accretion dominate. The result can look unexpected to an observer if they imagine void galaxies should be dormant. In reality, isolation can allow star formation to persist, but often at low efficiency, and the details depend on how gas is acquired and maintained. The outermost influence on star formation in a void galaxy is the state of the surrounding intergalactic gas. Most intergalactic gas at the present epoch is ionized by ultraviolet radiation. Ionized gas is warm and has pressure that resists collapse into small halos. For a low-mass halo, the ability to capture gas depends on the depth of its gravitational potential relative to the gas temperature. If the halo is too small, gas will not settle and will remain diffuse outside, leaving the halo with little fuel for star formation. This sets a threshold effect that is particularly relevant in voids, because the halo population is skewed toward low masses. Many void halos may sit near this threshold, making galaxy formation fragile. If a halo just above the threshold accretes gas, it can form a small galaxy. If it falls just below due to slower growth, it can remain dark. This sensitivity can create large differences in galaxy visibility within a void, even when the underlying halo distribution is smooth. For halos that do host galaxies, the gas must cool from the warm ionized state into a cold neutral phase and then into molecular clouds. Cooling depends on density and metallicity. In void environments, gas densities are lower, and galaxies can have lower metallicities, which reduces cooling efficiency. Metallicity here refers to the abundance of elements heavier than helium. These elements provide additional ways for gas to radiate energy away, enabling it to cool to lower temperatures. Lower metallicity slows the cooling path, making it harder for gas to become cold and dense. The conversion from atomic hydrogen to molecular hydrogen is also more difficult at low metallicity because dust abundance is lower. Dust helps shield gas from ultraviolet radiation and provides surfaces that catalyze molecular formation. Without sufficient shielding, molecular gas can be destroyed as quickly as it forms. This means a void galaxy can have a substantial reservoir of atomic hydrogen, while still forming stars slowly. The immediate star-forming fuel dense molecular gas can be a small fraction of the total. This can produce a galaxy that looks gas-rich, and yet only modestly active. In addition to cooling star formation, depends on compression and instability in the galaxy's gas disk. In dense environments, interactions and mergers can compress gas, strongly triggering bursts. In voids, such triggers are rarer. Compression instead comes from internal disk instabilities such as spiral arms and bars that concentrate gas, and from turbulence driven by feedback. A disk can become unstable when its self-gravity is strong enough relative to pressure and rotation to allow gas to clump. These instabilities can occur in isolated galaxies, and they can drive steady or episodic star formation. In low-mass galaxies, the disk may be less stable and more sensitive to feedback. A small burst of star formation can inject energy that heats and stirs gas, temporarily reducing star formation. Over time, gas can cool and settle again, allowing another burst. This creates an episodic pattern that does not require external interaction. In a void where the gas supply is not strongly perturbed by neighbours, such episodic cycles can dominate the star formation history. Gas supply remains the major uncertainty. Galaxies do not form stars indefinitely without replenishment, because star formation consumes gas, and feedback can expel it. In the standard picture, galaxies accrete gas from their surroundings, along filaments, and through more diffuse inflow. In voids, the filaments are weaker, but they are not absent. A void galaxy can still accrete gas, possibly from a faint internal filament, or from the surrounding intergalactic medium. The rate may be low, but over billions of years, even a low rate can sustain continued star formation. The inflowing gas may be relatively low in metallicity, which can dilute the galaxy's enriched gas and keep metallicity low. This can produce a galaxy that looks chemically young, even if it has been forming stars for a long time. Such a pattern can appear unexpected if one assumes chemical enrichment must proceed quickly. In isolation, Enrichment can be slow and can be balanced by inflow of less enriched material. The absence of environmental quenching processes is another crucial factor. In clusters, galaxies can lose gas through ram pressure stripping as they move through hot, dense intra-cluster gas. They can also be heated by the cluster environment and prevented from accreting new gas. In groups, tidal interactions can remove gas and disturb disks. In voids, these processes are weak. A galaxy can keep its gas for longer. This allows star formation to continue at late times, producing bluer colours and younger stellar populations on average than in dense environments for the same mass. This does not mean star formation is higher in absolute terms. It means it is less suppressed. For observers, this can make void galaxies look surprisingly active relative to expectations formed from studying cluster galaxies. When a claim arises that the Boötes Void revealed something never expected, it can sometimes refer to the presence of star-forming galaxies in a region assumed to be empty. Under the baseline physics, this is not unexpected. Voids are underdense, not sterile. The more interesting potential surprises are quantitative. If void galaxies show star formation efficiencies that are systematically higher than predicted by models for their halo masses, that would suggest that models may be misrepresenting gas cooling or molecular formation at low metallicity. If void galaxies show unexpectedly strong bursts without interactions that could point to internal instability mechanisms that are underrepresented in simulations. If void galaxies show an unusual prevalence of very low metallicity gas that could suggest that gas accretion in voids is more effective or more pristine than assumed. Each of these is a challenge in astrophysical modelling rather than in cosmology. The measurement side also shapes conclusions. Star formation rates are inferred from traces that respond on different timescales. Ultraviolet light traces recent star formation over tens of millions of years. Emission lines trace ionizing radiation from very young massive stars. Infrared emission traces dust heated by starlight. In low-dust void galaxies, infrared can be weak even when star formation exists, and ultraviolet can be less attenuated. Using a single tracer can therefore bias estimates. Confirming an unexpected star formation pattern requires multiple tracers and careful calibration. At this inward stage, the picture is that star formation in void galaxies is governed by internal regulation and slow gas supply, rather than by frequent interactions with low efficiency, driven by low metallicity and weak molecular formation, but with persistent activity enabled by the lack of stripping and by continued accretion. This sets up the next inward layer, which is the gas beyond the galaxies, the diffuse intergalactic medium within the void, because that gas is both the reservoir for future accretion and the primary component by volume in the void interior, and it is probed in different ways that can generate claims of surprising signals. The next inward region is the diffuse gas within the Boötes Void, the intergalactic medium that occupies most of the void's volume, and sets the conditions for how galaxies can accrete fuel. This gas is largely invisible in emission because it is too thin to shine strongly. Instead, its presence is inferred through the way it absorbs light from bright background sources and through the way it contributes to the overall baryon budget. In the standard picture, the void interior contains ionized hydrogen and helium at low density, with temperatures often in the range associated with photoionized gas. Compared to filaments and walls, the void gas is expected to be less dense, less enriched with heavy elements, and less shock heated. These expectations are not statements of absolute absence. They are statements about probability distributions and averages. A line of sight through a void can still intersect a denser patch associated with an internal filament, a small halo, or the outskirts of a galaxy. Such patches can produce absorption features that look surprisingly strong if one expects uniform emptiness. Understanding what could be revealed unexpectedly therefore requires understanding what absorption measurements actually sample. Absorption studies rely on the fact that atoms and ions absorb light at specific wavelengths. Hydrogen, the most abundant element, produces a strong absorption line known as Lyman alpha when neutral. Even in an ionized medium, a small fraction of hydrogen remains neutral, and that fraction can produce absorption. When light from a quasar passes through intergalactic gas, the gas imprints a series of absorption lines at wavelengths, shifted by the redshift of the gas along the line of sight. The pattern is a record of density variations. In higher density filaments, absorption lines are stronger and more frequent. In void interiors, the absorption should be weaker, on average reflecting lower density and a lower neutral fraction. However, the neutral fraction itself depends on density and on the ionizing radiation field. In very low density, gas recombination is rare, so the neutral fraction can be extremely low, weakening absorption even when the total gas mass is not negligible. This means that weak absorption can indicate either low density or high ionization, and disentangling the two requires modelling. Metal absorption lines provide additional information. Heavy elements such as carbon and oxygen are produced in stars and dispersed into gas by winds and outflows. In voids, fewer galaxies and lower star formation activity imply less enrichment on average. Therefore, metal lines should be rarer and weaker. If metal lines are detected in the deep interior, it suggests that enrichment has reached there either from local faint galaxies, from outflows travelling long distances, or from earlier epochs, when enrichment events were more widespread. None of these is impossible. Over billions of years, metals can be transported far from their sources, especially in low-density regions where resistance is low. Yet the level of enrichment remains an empirical question. A detection of unexpectedly strong metal absorption in a sightline believed to pass through the void core could therefore appear surprising. To interpret it, one must determine whether the sightline truly passes through the deepest underdensity, and whether the absorber is associated with a hidden galaxy or halo. The geometry of absorption sampling is a major limitation. Each background source provides a narrow pencil beam through the void. Even a large void can be sampled by only a handful of suitable quasars. The distribution of quasars on the sky is not controlled by the observer. It is fixed by nature. As a result, the sightlines may cluster in some parts of the void and miss others. A single strong absorber along one sightline can be interpreted as evidence of unexpectedly dense gas, but it may simply indicate that the sightline intersects an internal filament. Simulations predict that such filaments exist and that they can host higher density gas than the void average. Therefore, the significance of an absorption feature depends on how typical it is across many sightlines. With few sightlines, uncertainty is large. This is why many robust void gas results come from stacking many voids in large surveys, measuring average absorption profiles as a function of distance from void centers. For a named void like Boötes, the more realistic goal is to constrain whether gas is present at the expected level and whether its ionization and enrichment are broadly consistent with void environments. Another observational approach involves neutral hydrogen emission at radio wavelengths. Neutral hydrogen emits at a wavelength of 21 centimeters. This emission is routinely used to map cold gas in galaxies, but detecting truly diffuse intergalactic hydrogen in emission is far more difficult because the signal is weak. In a void where densities are low, diffuse emission is essentially beyond current direct detection for most of the volume. However, radio surveys can reveal gas-rich galaxies that are optically faint. These galaxies can alter the interpretation of void gas because they indicate where cold gas reservoirs exist and can serve as potential sources of enrichment. If a void contains more gas-rich dwarfs than optical surveys reveal, the void may be less empty in baryons and may have more internal enrichment sources than assumed. Yet this does not necessarily change the baseline that most baryons remain ionized and diffuse. The thermal state of void gas is set by photoheating from ultraviolet radiation and by adiabatic cooling as the gas expands. In underdense regions, adiabatic cooling is more effective because the gas experiences more expansion relative to average. This can keep temperatures lower than in filaments where gas is compressed and shock heated. Lower temperature in itself does not guarantee higher neutral fractions, because ionization is controlled by radiation and density. In fact, low density tends to keep gas highly ionized. Therefore, the expected void intergalactic medium is a low-density, highly ionized, moderately warm gas that is faint in emission and subtle in absorption. This is why void gas is sometimes described as missing in observational maps, even though it is expected to exist. If something never expected is claimed, one plausible category is an absorber that implies unexpectedly high density or unexpectedly high metal enrichment deep in the void. Another category is the absence of absorption, where models predict some implying a lower baryon density or a higher ionization state than assumed. Both categories are sensitive to modeling. To translate an absorption line into density, one needs an ionization correction, an estimate of the fraction of an element in a given ionization state. This depends on the ultraviolet background spectrum gas temperature and density. For hydrogen, one needs the neutral fraction. Small changes in assumed ultraviolet background intensity can change neutral fraction significantly in low-density gas. Therefore, interpreting void absorption requires acknowledging uncertainty in the background radiation field. Similarly, interpreting metal lines requires assumptions about metallicity distributions and about the presence of multiphase gas. A single absorber can be a dense small cloud or a more extended diffuse structure. Without additional lines or multiple ions to constrain conditions, the geometry remains uncertain. This is why a calm model-aligned interpretation treats void gas observations as constraints with wide error bars. A few strong absorbers inside Boötes would not necessarily be a contradiction. They could be internal filaments. A few weak absorbers would not necessarily mean baryons are missing. They could be highly ionized gas. Only a systematic pattern across many sightlines showing absorption strength consistently outside the predicted distribution for void environments would point to tension. Even then, one must consider whether the void definition used in the analysis matches the one used in simulations, and whether the sightlines truly sample the core. At this inward stage, the diffuse gas is recognized as the quiet bulk of the void present, but hard to see, and capable of producing occasional features that feel surprising when seen in sparse sampling. This prepares the next inward layer, which is the dark matter structure within the void, because dark matter sets the gravitational potential that shapes both the gas distribution and the motions of the galaxies that exist. And because distinguishing light emptiness from mass emptiness is central to judging whether any revelation is genuinely unexpected, the next inward region is the void's dark matter structure, the component that dominates the gravitational field and determines whether the Boötes void is truly extreme in mass or primarily extreme in light. Dark matter does not emit light, so it is inferred through its gravitational influence on galaxies' gas and light from more distant sources. In the standard framework, dark matter forms a connected cosmic web. Voids are under dense regions in that web, not holes. The web inside a void is diluted with fewer massive halos and weaker filaments, but it remains present. This distinction between diluted and absent is central. A void that is very empty of luminous galaxies can still contain many low-mass dark matter halos that either host very faint galaxies or host no luminous galaxies at all. Therefore, an apparent revelation based on galaxy scarcity often reduces to the question of how strongly galaxy counts trace the underlying mass in low-density environments. The most direct probe of mass independent of whether it forms stars is gravitational lensing. Mass bends light. When background galaxies are viewed through a foreground mass distribution, their apparent shapes are slightly distorted. In dense regions such as clusters, the distortion can be large enough to detect around individual objects. In voids, the signal is much smaller because the mass deficit creates a subtle stretching pattern that indicates lower than average mass along the line of sight. Detecting this signal requires averaging over many background galaxies and often stacking many voids. For an individual named void, like Boötes' weak lensing is challenging because the void covers a large sky area. The signal is low and systematics in shape measurement can dominate. Even so, lensing remains conceptually important because it clarifies what would count as truly unexpected. If lensing were to show that the mass deficit in Boötes is as extreme as the luminous deficit, that would suggest either an unusually deep mass underdensity or a failure in the expected relationship between galaxy bias and mass. If lensing instead shows a moderate mass deficit, it supports the conventional view that the void's dramatic appearance in galaxy surveys is amplified by tracer bias and by the suppression of luminous galaxy formation. Another mass-related probe is the velocity field because peculiar velocities arise from gravitational potential gradients. In voids, the potential is shallow compared to dense regions and matter flows outward. The amplitude and pattern of this flow depend on the integrated mass deficit. If one can infer the velocity profile from redshift space distortions, one can constrain the mass profile. This method is indirect and sensitive to assumptions about galaxy bias and redshift errors, but it provides a way to test whether the void's mass under density matches expectations. A strong outflow signal would imply a deeper mass deficit, while a weak outflow signal would imply a shallower one. Again, the limitation is that the galaxy tracers used to infer the velocity field are sparse in the void interior, so the inference often relies on galaxies near the boundary rather than deep core tracers. Within simulations, the dark matter structure inside voids is characterized by a shifted halo mass function. The number density of halos drops, and the distribution shifts towards smaller masses. Massive halos are rare. Low-mass halos are more common, but many of them are below the thresholds at which gas can cool and form stars efficiently. This creates a population of dark halos. Their abundance is not directly observable, but their existence is expected. They contribute to lensing and to the gravitational field that shapes the motions of visible galaxies. They also provide potential sites for gas accumulation, even if star formation is weak. In some cases, a dark halo may host a gas-rich but optically faint galaxy detectable through neutral hydrogen emission. In other cases, it may host only diffuse ionized gas. A frequent source of confusion is to equate galaxy voids with mass voids. Galaxies are bias tracers. They preferentially form in higher density regions, and the bias becomes stronger for more luminous galaxies. In an underdense region, the abundance of luminous galaxies can drop dramatically even when the mass under density is moderate. This is because the formation of high-mass halos is suppressed, and because the efficiency of galaxy formation in low-mass halos can be reduced. As a result, a galaxy-defined void can appear nearly empty. This is expected. In model terms, the void in the galaxy field is deeper than the void in the mass field. Therefore, a claim that a void is model-breaking based on its galaxy emptiness must be evaluated by comparing to simulations that include the same galaxy selection, not by comparing to mass field expectations. The structure of dark matter within the void also includes weak internal filaments. These filaments are not prominent in mass density maps unless one looks at appropriate smoothing scales. They can host a slightly higher density than the surrounding void, and they can be the sites where the few void galaxies reside. This arrangement can create the impression that galaxies inside the void are strangely aligned, or that the void contains unexpected structure. In fact, such internal structure is a model prediction. It reflects that the initial density field contains fluctuations on many scales, and even in an underdense region, small-scale fluctuations can persist. The void is underdense in its mean, but it is not featureless. What would count as a genuinely unexpected revelation in the dark matter context would be a mass profile or a halo population inconsistent with the standard initial conditions and growth. For example, if the void's mass deficit inferred through lensing and dynamics were far deeper than the model allows for the surveyed volume, that would challenge the standard parameter set or the assumption of Gaussian initial fluctuations. Another possibility would be an internal mass concentration, or cluster, deep in the void core that is too massive to be consistent with the halo mass function in such an environment. Such a case would demand careful membership verification, because boundary misclassification and projection effects can make a structure appear internal when it is not. But if confirmed, it would be a notable outlier. In practice, most apparent revelations in void contexts trace back to the difference between mass and light. The Boötes Void is dramatic in galaxy maps because bright galaxies are scarce. The dark matter field likely remains a diluted network with many low-mass halos and a moderate mass under density. This interpretation remains consistent with the success of standard simulations in reproducing void statistics when tracer selection is matched. Yet uncertainties remain because direct mass probes are difficult. This is why voids remain interesting. There are extreme environments where the mapping from mass to light is stressed, offering a sensitive test of galaxy formation prescriptions. At this inward stage, the emphasis is that dark matter provides the gravitational reality of the void, but observations often show the void through biased tracers. Separating these is essential for judging whether anything is truly unexpected. The next inward step is to focus on dynamics more directly describing how the void's predicted outflow and redshift space distortions offer a practical observable bridge from mass deficit to measurable signals, and how these signals can either support standard expectations or hint at a mismatch when interpreted carefully. The next inward region is the void's dynamics, where the Boötes Void is treated as a gravitationally defined underdensity that should leave measurable signatures in the motions of galaxies and in the way galaxy positions appear in redshift space. In the standard picture, an underdense region has a weaker inward gravitational pull than average. This means that the general expansion of space is less slowed within the region. Matter therefore flows outward relative to the void center, producing a coherent outflow pattern. This outflow is not a separate expansion and not a sudden push. It is a persistent, gentle consequence of gravity acting on a density gradient over billions of years. Because redshift measurements combine cosmic expansion and line-of-sight peculiar velocity, this outflow can distort the apparent shape of the void in redshift space, offering one of the few practical ways to connect the void's mass profile to an observable signal. Peculiar velocity is the key term. A galaxy's observed redshift reflects the expansion of space between the galaxy and the observer, but it also includes the component of the galaxy's own motion toward or away from the observer. In dense regions, peculiar velocities are often random motions within groups and clusters. In void contexts, the dominant pattern is coherent. Galaxies tend to move away from the underdense center. This creates a systematic shift in redshift space positions. If a galaxy near the far side of the void is moving away from the void center, it may also be moving away from the observer, along the line of sight, adding to its redshift and making it appear slightly farther away. If a galaxy near the near side is moving toward the observer relative to the void center, it can have a reduced redshift and appear slightly closer. The net effect can stretch the void along the line of sight in redshift space depending on geometry. The details depend on the void's shape and on how the velocity field aligns with the observer's line of sight. This is why voids can look different in different survey slices. In practice, directly measuring peculiar velocities for galaxies at the distances relevant to Boötes is difficult. It requires independent distance indicators, which are uncertain at those distances. Therefore, the main dynamic inference is statistical and relies on redshift space distortions. One common method is to measure the distribution of galaxies around void centers in redshift space and compare it to models that predict how density and velocity fields distort that distribution. Analysts compute the void galaxy cross-correlation function and examine its anisotropy, the difference between clustering along the line of sight and clustering across the line of sight. This anisotropy encodes the velocity field. In ensembles of voids, this method can measure average outflow profiles and can constrain the growth rate of structure. For a single void like Boötes, the same logic applies, but the statistical power is lower because the number of tracer galaxies is limited, especially in the interior. Most of the signal comes from galaxies near the boundary, and just outside it where galaxy density is higher. The expected velocity profile around a void has a characteristic form. Near the center, where density is lowest, the outflow relative to the mean is strongest, though this region is sparsely traced. Moving outward, the outflow decreases as one approaches the boundary where density rises. If the void is compensated by an overdense ridge near the boundary, the velocity field can show a transition as the gravitational pull of the ridge influences motions. Beyond the ridge, motions may be influenced more by surrounding large-scale structures than by the void itself. The exact shape of this profile depends on void size, depth, and environment. Large voids tend to have smoother profiles and less extreme mass deficits than smaller, deeper voids, but they still produce coherent flows. Anisotropy in the observed profile is expected because voids are not perfect spheres and because surrounding structures are not uniformly distributed. A void may have a stronger outflow in a direction that opens into broader underdensity and a weaker outflow toward a nearby massive filament. Dynamic inferences are complicated by redshift measurement error and by the fact that galaxies are biased tracers. Redshift errors smear galaxy positions along the line of sight, reducing apparent anisotropy. Galaxy bias changes the relationship between the observed galaxy density profile and the underlying mass density profile. If bias is stronger in underdense regions, the galaxy profile can appear deeper, and the predicted velocity field based on the galaxy profile alone can be misleading. Therefore, models often include bias parameters and calibrate them using simulations or using larger-scale clustering measurements. In void analyses, a robust approach is to use mock catalogues built from simulations, apply the same void finder and selection, and measure the same anisotropy. If the mocks reproduce the observed pattern, the dynamics are consistent with the model. If not, one must determine whether the mismatch arises from bias modelling from survey systematics or from a genuine difference in the mass field. A related concept is the growth rate of structure, which describes how quickly density fluctuations grow over time under gravity. The growth rate affects peculiar velocities. If growth is faster, velocities are larger for a given density field. If growth is slower, velocities are smaller. Voids have been proposed as probes of growth because their outflow pattern depends on gravitational dynamics in an underdense regime. Tests using many voids in large surveys generally find consistency with standard gravity within uncertainties. For Boötes, the power to constrain growth is limited, but the void can still serve as a qualitative check. If one inferred an outflow much stronger than expected, it could suggest a deeper mass deficit or a difference in growth. If one inferred an outflow much weaker, it could suggest a shallower mass deficit or stronger bias. However, because direct measurement is hard, such inferences would need to be corroborated with other probes. A claim that the Boötes Void revealed something never expected could in principle involve dynamics. For example, if the void shape in redshift space implied an outflow pattern inconsistent with standard predictions, or if peculiar velocity estimates suggested a mass deficit beyond allowed statistical expectations. Yet in practice, the more common situation is that void dynamics are under-constrained for a single void, and apparent anomalies can arise from redshift space interpretation errors from incomplete sampling or from the void's irregular geometry. Therefore, dynamics are most persuasive when the measurement is framed as a constraint with uncertainty, and compared to redshift space simulations that replicate the survey. The key value of dynamics in this narrative is that it offers a bridge from the void's mass deficit to measurable signatures without relying solely on galaxy counts. If galaxy counts suggest extreme emptiness, dynamics can test whether the gravitational field is equally extreme. If dynamics indicate only moderate outflow, it supports the view that the void is amplified in the luminous tracer. If dynamics indicate strong outflow, it suggests a deeper mass deficit. Either way, dynamics provide a way to refine what is truly being revealed. With dynamics established as a potential test and as a source of subtle systematics, the next inward step is to clarify what the phrase "never expected" can and cannot mean in a scientific context. That requires defining the categories of observations that are commonly framed as anomalies in void studies, and specifying what would be required for such observations to constitute real tension with models rather than the expected behavior of rare environments combined with sparse sampling. The phrase "never expected" often functions as an emotional summary rather than a scientific claim. To make it scientific, it must be translated into a specific statement about an observable that lies outside the predicted distribution under a defined model and defined measurement pipeline. The next inward region is therefore the set of observation categories that can produce a feeling of surprise in the Boötes Void, and the conditions under which such a surprise would represent genuine tension, rather than the ordinary behavior of a sparse environment. In void research, most supposed surprises fall into one of a few types: an unexpectedly empty galaxy census, an unexpectedly rich interior structure, an unexpected galaxy population or extreme galaxy properties, unexpected gas absorption signatures or unexpected gravitational signals. Each type can be explained by conventional effects in many cases, but each also has a pathway to real tension if it survives careful definition and statistical testing. The first category is the overall emptiness itself. A claim that the Boötes Void is too empty can mean that the number density of galaxies above a given luminosity threshold is far below what the model predicts for voids of that size within the surveyed volume. The necessary elements for this to be meaningful are a clear tracer definition, a clear volume definition, and a model prediction that includes the same selection and geometry. If the void is defined using bright galaxies, then the model must use a mock catalogue with the same brightness cut. If the void is defined using a particular survey footprint, then the model must incorporate that footprint. Only then does one compare the void's extremeness to the distribution of voids in the mocks. If the void lies far into the tail with a probability so low that it is inconsistent with the survey volume, then one has tension. If it lies in the tail but within expected extremes, then it is an example of a rare but expected structure. Most dramatic voids become less anomalous when treated in this matched way, because the look elsewhere effect and tracer bias are strong. The second category is internal structure that seems too coherent. If galaxies inside the void appear to form a filament, a wall or a group, it can feel inconsistent with emptiness. Models predict weak internal structure, so the presence of a faint internal filament is expected. The surprise would be if the internal structure is dense enough to imply a massive halo population, or a mass concentration inconsistent with the void's claimed depth. This requires measuring not just the galaxy arrangement, but the implied mass either through galaxy dynamics, group richness, or lensing. A small group of dwarfs is not a contradiction. A rich cluster deep in the core would be harder to reconcile. In most cases, apparent internal structure is a boundary intrusion or a consequence of the void being defined too broadly. Therefore, membership verification and local density classification are essential before labeling the structure unexpected. The third category is the presence of an apparently massive or evolved galaxy in the deep interior. Such a galaxy can seem like it does not belong. Models do allow rare high-mass halos in underdense regions, but the frequency should be low. A single massive galaxy can be an outlier. Multiple such galaxies deep in the core would be more challenging. The path to tension requires verifying the galaxy's distance and environment, estimating its halo mass, and comparing the occurrence rate to model predictions for the same void definition. Even then, one must consider whether the galaxy selection is biased toward finding unusual objects. In a void, observers may focus attention on any object that exists, increasing the perceived significance. The proper comparison is the distribution of galaxy masses in void environments, in simulations and in large survey samples, not the impression from one object. The fourth category involves extreme galaxy properties that suggest unusual gas accretion or unusual evolutionary histories. Examples include very low metallicity for a given stellar mass, unusually high gas fractions or star formation rates that are high relative to mass and expected gas supply. These extremes can be plausible in voids because of slow enrichment, reduced stripping, and intermittent accretion. The route to a true anomaly is again frequency and degree. If the void environment produces an excess of such extreme galaxies beyond what models reproduce, then models may be missing physics. This would typically be a galaxy formation modeling issue, not a cosmological issue, because these properties depend on cooling feedback in the ultraviolet background. Still, such a mismatch can feel like a model failure to an observer if they treat the model as a single monolithic prediction, rather than as a coupled set of cosmology and baryonic prescriptions. The fifth category is gas absorption, that suggests unexpectedly dense or enriched intergalactic medium in the core. A strong hydrogen absorber or a metal-enriched absorber along a sightline through the void can feel like a contradiction. Yet models predict internal filaments and halos that can produce such absorbers. The difference between expected and unexpected depends on how common these absorbers are relative to void expectations. With few sightlines, a single absorber is not decisive. A systematic pattern across multiple independent sightlines showing absorber strengths inconsistent with predicted distributions would be more meaningful. Even then, ionization modeling uncertainty is large in low-density gas, so a robust anomaly would need constraints from multiple ions and from independent measures of nearby galaxies that might be associated with the absorber. The sixth category is gravitational signals such as lensing or integrated effects on background radiation. A void that appears to produce an unusually strong lensing signal or an unusually strong imprint on the cosmic microwave background could be framed as unexpected. Here the challenge is that the signals are small and dominated by noise and by chance alignments. A strong claim would require careful statistical handling, ideally using ensembles of voids and comparing to simulations. For a single void, the chance of misinterpretation is high. Across all categories, the conditions for turning surprise into tension are consistent. One must specify the observable and how it is measured. One must specify the model prediction for that observable under the same measurement pipeline. One must quantify uncertainty and account for selection and multiple testing. One must seek replication in independent data or methods. Without these, a claim remains a narrative of novelty rather than a tested discrepancy. In the Boötes context, the safest interpretation is that the void is an extreme but plausible underdensity, whose dramatic appearance is amplified by the use of luminous galaxy tracers. Potentially surprising details, whether a particular galaxy or a particular absorber, are best treated as test cases for galaxy formation and gas physics in low-density environments, rather than as immediate threats to cosmological structure formation. This does not diminish their value. It clarifies what kinds of follow-up can be decisive. The next inward step is to examine the specific systematics that most often produce false surprises in void work, because in sparse regions the boundary between a real signal and an artifact is thin, and understanding the common pitfalls is essential before any unexpected feature can be judged with confidence. In a region as sparse as the Boötes Void, the most convincing sounding surprises can arise from the simplest observational and analysis pitfalls. The next inward region is therefore a careful accounting of systematics that can mimic an unexpected discovery, either by making the void look emptier than it is by placing objects inside the void that are actually outside, or by exaggerating the significance of sparse patterns. These systematics are not generic caveats. They shape the specific story of what can be said about a named void and what cannot. A disciplined reading of any claim about a revelation inside Boötes begins by asking whether the claim survives the most common failure modes in void mapping: incompleteness, surface brightness, bias survey, geometry, redshift, space, distortions, boundary definition, sensitivity, and small number statistics. The first systematic is incompleteness in the galaxy catalogue. A void is defined by a deficit of galaxies, so any deficit caused by missing data can look like a void. Imaging incompleteness can occur when the exposure depth varies, when the sky background is higher in some fields, or when detection algorithms fail near bright stars. Spectroscopic incompleteness can occur when not all imaging targets receive spectra, when spectra fail for faint or diffuse galaxies, or when fibers cannot be placed near each other. If the Boötes region had lower spectroscopic completeness than surrounding areas, it could appear emptier in three-dimensional maps. Modern surveys provide completeness masks and weights to correct for this, but older catalogues could be more vulnerable. Even in modern data, incompleteness is often a function of position and brightness, which can imprint subtle patterns. A robust void claim therefore uses a volume-limited sample with high completeness and demonstrates that the void persists when completeness corrections are applied. Surface brightness bias is the second systematic and is especially potent for void interiors. A galaxy can be intrinsically large and diffuse with low surface brightness. Such galaxies can be underdetected even in deep imaging because detection depends on contrast. In voids, where galaxies may be low mass and low star formation, low surface brightness systems may be relatively common. If these galaxies are missed, the void appears more extreme. This is a likely contributor to the dramatic appearance of voids in early optical surveys. The mitigation is to use specialized low surface brightness searches, deeper imaging, and complementary tracers such as neutral hydrogen. Yet even these mitigations are incomplete because a gas-poor diffuse dwarf can be missed in both optical and radio. Therefore, any statement about absolute emptiness must remain conditional on detectability thresholds. Survey geometry and masking form a third systematic. Surveys avoid bright stars and have irregular footprints. If the void region overlaps a mask or lies near a survey edge void, finding can be biased. The algorithm might treat unobserved regions as empty, enlarging the void, or it might truncate the void boundary. Proper analysis uses the survey mask and constructs random catalogues that match the angular and radial selection, allowing densities to be estimated relative to the expected sampling. For a named void, it is also important that it appears in multiple surveys with different footprints, reducing the chance that it is driven by a specific mask. When a claim is made about a feature inside the void, such as an internal filament, or an unexpected object distribution, one must check that the feature is not aligned with variations in survey depth or with masked zones. Redshift space distortions and distance errors create a fourth systematic. Peculiar velocities can shift galaxies along the line of sight in redshift space, moving them across a void boundary. A galaxy near the boundary might be placed inside the void in redshift space, even if it is outside in real space or vice versa. This is particularly relevant for galaxies in groups where random motions can be significant. It is also relevant for coherent flows around the void, which can stretch or compress the apparent void shape. Mitigation involves working consistently in redshift space and comparing to redshift space simulations or applying reconstruction methods. However, reconstruction itself introduces modelling assumptions. Therefore, when a claim hinges on whether a specific galaxy is truly deep inside Boötes, it must either use additional distance information beyond redshift or accept that membership has some probability rather than certainty. Boundary definition sensitivity is the fifth systematic. A void boundary is drawn by a chosen algorithm and threshold. Change the threshold or algorithm and the void changes. A galaxy can move from interior to boundary, or from boundary to exterior depending on definition. This matters because a claim of unexpectedness is often strongest when an object is described as deep in the void core. If the object lies near the boundary under one definition, its surprise value diminishes. Therefore, robust claims use multiple void definitions or continuous environment metrics such as local density estimators to show that the object resides in a low-density environment regardless of boundary choice. For Boötes, where the boundary is irregular and the void may connect to adjacent under-dense regions, definition sensitivity can be large. This can also affect size claims. A large void under a connected under-density definition may appear too large compared to model expectations if the model comparison uses a different definition. Small number statistics shot noise is the sixth systematic and often the most psychologically influential. In a void interior, the number of galaxies above a brightness threshold can be so small that random fluctuations dominate. A few additional galaxies found by a deeper survey can change the inferred density dramatically. Similarly, the appearance of a filament can be created by a handful of points. Human perception tends to interpret sparse alignments as meaningful patterns. Statistical tests can evaluate whether an alignment is significant relative to a random distribution conditioned on the same number of points and the same survey geometry. Without such tests, narrative claims about internal structure can be misleading. This also applies to absorption studies. With one or two background sightlines, a single absorber can be framed as unexpected. In reality, it could be a typical intersection with an internal filament the simulations predict. Sparse sampling makes surprises easy to narrate and hard to confirm. Calibration systematics form a seventh category for claims about galaxy properties. Star formation rates inferred from ultraviolet emission lines or infrared depend on assumptions about dust and stellar populations. In void, galaxies' dust content can be low, making standard dust corrections inappropriate. Metallicity measurements depend on emission line calibrations that can differ systematically by tenths of a dex. Gas mass measurements from radio emission depend on distance and on conversion factors. If a galaxy inside Boötes is described as extraordinarily metal-poor or extraordinarily gas-rich, the claim must be checked against calibration uncertainties and ideally confirmed with multiple independent methods. Otherwise, the extremeness can be overstated. Finally, confirmation bias and selection bias can shape what is reported. A named void draws attention. Observers may preferentially publish unusual objects found within it, while ordinary objects receive less attention. This can create a literature impression that the void contains many anomalies, when in fact the anomalies are a selected subset. The corrective is systematic surveys of void interiors with well-defined selection and comparison samples. When these systematics are applied to any claim of revelation, the number of plausible interpretations often narrows. An object thought to be deep inside may be near the boundary. An apparent absence may reflect surface brightness bias. An internal filament may be consistent with predicted substructure. A strong absorber may be associated with an unseen dwarf galaxy. This does not mean surprises cannot exist. It means surprises must be resilient to these checks. The next inward step is therefore to move from systematics to statistical expectation, because even after perfect measurement, rare extremes exist. Understanding how a single prominent void should be judged requires a clear grasp of cosmic variance, the look elsewhere effect, and how model predictions are framed as distributions rather than single outcomes. After addressing systematics, the next inward region is the statistical meaning of one prominent void and one set of potentially surprising findings within it. In the standard cosmological picture, the large-scale structure is a realization of an initial random field. The field has well-constrained statistical properties, but any finite region of the universe shows a particular pattern that can include rare extremes. This is the core reason a named void can feel like an exception while still being consistent with the model. The model does not predict that the nearby universe must look average. It predicts a distribution of possible structures, including tails. The question is whether the Boötes Void and any claimed interior feature lie within the expected tail given the survey volume and the observational selection, or whether they lie so far into the tail that the probability becomes implausibly small. Cosmic variance is the first statistical concept. It describes the natural variation between different regions of the universe due to randomness in the initial conditions. Even if the model is correct, two survey volumes of the same size can contain different numbers of large voids and clusters. The variation is larger for smaller survey volumes and for rarer structures. Because the Boötes Void is large, it is inherently a rare structure, so the variance in its occurrence is significant. This means that finding one large void in the nearby universe is not by itself surprising. The critical detail is the effective survey volume within which the void was identified. If the survey volume is small, the presence of one extreme void could still be consistent. If the survey volume is very large and yet the void is more extreme than any simulation predicts, then there could be tension. The look elsewhere effect is the second concept. Named structures are often identified by searching maps for the most conspicuous features. If one searches across many positions and distance shells, one will find something extreme somewhere. The probability of finding the most extreme object is not the same as the probability that a randomly chosen object is that extreme. Therefore, when evaluating whether Boötes is too extreme, one must compare it not to the distribution of a typical void, but to the distribution of the most extreme void in a survey of that size. This often reduces apparent tension. A structure that seems impossibly rare under the typical distribution can be expected under the maximum distribution once the search process is considered. Tracer dependence is the third concept. Voids defined by bright galaxies are deeper and larger than voids defined by fainter galaxies, because bright galaxies are more biased tracers. Therefore, the statistical distribution of void properties depends on the tracer. A model prediction must match the tracer selection. If one compares a bright galaxy-defined void to a mass field void distribution, the void will appear too extreme because the comparison is mismatched. Correct comparison uses mock catalogues that include galaxies with the same luminosity cut and the same survey selection, and then applies the same void finder. Only then does one ask where Boötes lies in the mock distribution. Many claims of model-breaking voids fade under this matched analysis, because the model reproduces the tail once bias and selection are included. The distribution itself has multiple dimensions. A void has a size, a depth, a shape, and a profile. These properties are correlated. Large voids tend to have shallower mass deficits than small deep voids, though their galaxy deficits can still be strong. Shapes are often elongated and irregular due to surrounding structure. Profiles can show compensation ridges. If a claim of surprise relies on a combination of properties, The correct test uses the joint distribution, not separate one-dimensional tests. For example, a void might be large and appear very empty in bright galaxies. Each property alone may be within expectations, but the combination might be rarer. Conversely, the combination might be expected once correlations are included. Without joint modelling, the perceived rarity can be misestimated. The same logic applies to interior features. If an unusual galaxy is found inside the void, one must ask how often such galaxies occur in voids in general. Unusual galaxies exist everywhere. The question is whether voids change the frequency. A single object cannot answer that. One needs a sample of void galaxies and a control sample matched in mass and observational limits, then a statistical comparison. If the frequency of extreme properties is higher than models predict, the tension is likely with galaxy formation prescriptions, not with cosmology. If the frequency is consistent, then the object is an example of the distribution's tail. Statistical evaluation is typically done through simulations and mock surveys. A simulation provides many realizations of the cosmic web. By applying a survey mass selection function and noise model, one produces mock observations. Voids are then identified in the mocks using the same algorithm. This yields a distribution of void properties and interior galaxy properties under the combined assumptions of cosmology and galaxy formation modelling. One then asks how often a Boötes-like void occurs. If it occurs frequently enough, the void is consistent. If it is rare, one examines whether changing void definition or tracer selection alters the conclusion. If it remains rare across reasonable choices, one examines whether parameter variations can increase its probability. Often the result is that the void is not impossible, but sits in a tail that is sensitive to assumptions. This sensitivity is itself informative. If a void's apparent extremeness depends strongly on the brightness threshold, then it is likely driven by bias rather than by an extreme mass deficit. If it depends strongly on survey geometry, then it may be partly artifact. If it remains extreme across tracer thresholds and definitions, it may reflect a truly deep underdensity. But even then, one must quantify probability properly. A probability of 1 in 1,000 may sound small, but in a survey that effectively tests thousands of independent regions, such an event is expected. Therefore, absolute statements like never expected are rarely justified without explicit accounting. In a calm scientific reading, the Boötes void is treated as a notable but not necessarily model-breaking structure. Its existence is expected as part of the distribution of voids. Any unexpected interior feature is treated as a candidate outlier that must be evaluated in frequency terms and with matched comparisons. This statistical framing does not dismiss surprise. It redefines surprise as a quantified discrepancy rather than as a narrative impression. With this framing, the next inward step is to translate the standard model into concrete observable predictions for void profiles, compensation lensing signals, and environment-dependent galaxy properties. This translation matters because it provides a clear checklist of what should be measured to decide whether a claimed revelation is merely a rare but expected draw or a genuine mismatch that remains after selection and statistical context are applied. To decide whether a claim about Boötes is unexpected in a meaningful way, the model must be expressed in the same language as the data. The next inward region is therefore the set of standard model predictions stated as observables, density profiles in galaxies, and mass, the presence or absence of compensation ridges, the expected lensing signature, the expected redshift space, anisotropy, and the expected shifts in galaxy properties as a function of environment. These predictions are not exact templates for a single void, but they define relationships among measurable quantities. A real mismatch is a broken relationship that persists after matching definition, selection, and geometry. The first prediction is the difference between galaxy underdensity and mass underdensity. In a bright galaxy sample, a void can appear extremely empty. The model predicts that the mass deficit is usually less extreme because galaxies are biased tracers. Therefore, the void's galaxy density profile measured by counting galaxies as a function of radius from the void center is expected to be deeper than the mass profile. The observable consequence is that if one measures weak lensing around voids, the inferred surface mass density deficit should be shallower than the galaxy deficit. In ensemble measurements, this is generally what is sought. For a single void, the expectation still holds, though the measurement is difficult. A claim that the void is too empty in a way that challenges models must therefore specify whether the mass deficit, not merely the galaxy deficit, is too large. The second prediction is the shape of the void profile. In the model, a void typically has a low-density core and a transition region where density rises toward the boundary. The rise can be smooth. In some cases, matter accumulates near the boundary, producing a ridge where density exceeds the mean. Whether this ridge is present and how strong it is depends on the void's environment and on how the void is defined. The observable signature is a bump in the galaxy density profile near the boundary and a corresponding feature in the lensing profile. A compensated void shows a clear ridge. An uncompensated void shows a weaker or absent ridge and remains underdense on larger scales. For Boötes, the surrounding web suggests some boundary enhancement, but the degree of compensation in mass remains uncertain. If a claim involves an unexpectedly sharp boundary or an unexpectedly high ridge, it must be compared to mock surveys that include the same tracer selection and void finding method, because ridge strength in galaxies depends strongly on bias. The third prediction is the redshift space distortion pattern. Given a density profile, the model predicts an outflow velocity field that produces a characteristic anisotropy in the void galaxy cross-correlation function. The observable is the difference in the distribution of galaxies around void centers along the line of sight compared to transverse directions. In the model, this anisotropy is linked to the growth rate of structure. Therefore, a joint measurement of density profile and anisotropy provides a consistency test. If the anisotropy implies a velocity field that is inconsistent with the density field under standard gravity, then there is a discrepancy. However, because bias and redshift errors can mimic changes, a robust discrepancy requires careful modelling. For Boötes, this means the void's apparent elongation or compression in redshift space must be interpreted with simulations that replicate the survey and include realistic peculiar velocities. The fourth prediction is the lensing signal. A void produces a negative convergence signal, meaning a deficit in projected mass density. In weak lensing terms, the tangential shear pattern around voids is expected to be small and typically negative in a specific convention reflecting the underdensity. The signal depends on void size depth and the redshift distribution of background sources. In practice, lensing signals are measured by stacking many voids. If a single void is claimed to produce a strong lensing signal, the claim must address shape noise, intrinsic alignments and systematics in shear measurement. A robust lensing-based claim of unexpected mass deficit would require that the signal is strong relative to expected noise and consistent across independent shape catalogues and analysis choices. The fifth prediction is the environment dependence of galaxy properties at fixed mass. In standard galaxy formation models embedded in standard cosmology, void galaxies are expected to be more frequently star-forming, more gas-rich and lower in metallicity at fixed stellar mass compared to galaxies in denser environments. The observable test requires matching galaxies by stellar mass and redshift, then comparing distributions of star formation, rate gas fraction, and metallicity. If Boötes Void galaxies show properties outside the predicted range, the likely implication is that the model's baryonic prescriptions need adjustment, such as gas accretion rates, feedback strength, molecular gas formation at low metallicity, or ultraviolet background effects. This is a tractable form of mismatch. It is not a claim that gravity fails. It is a claim that galaxy formation in low-density environments is not fully captured. The sixth prediction is internal structure. The model predicts that void interiors contain weak substructure, including internal filaments and small halos. The observable manifestation is that void galaxies may not be uniformly distributed and may show alignments or clustering at low level. The test is whether the level of clustering matches mock catalogues. If Boötes shows no internal structure at all, even in deep surveys, it could indicate stronger suppression of halo occupation than assumed. If it shows stronger internal structure than expected, it could indicate that the void definition includes regions that are not truly deep under densities, or that the halo population is richer. Either outcome is interpretable within model uncertainties if treated carefully. The seventh prediction is baryon distribution and enrichment. In the model void, gas is expected to be less enriched and to show weaker absorption on average. Observationally, one measures absorption line statistics as a function of distance from void centers. A significant deviation could indicate more widespread enrichment, perhaps from winds traveling farther than expected, or different ionization conditions. Again, the implication is likely astrophysical rather than cosmological. Taken together, these predictions form an observable checklist. A claim that the Boötes Void revealed something never expected should map onto one or more of these measurable relationships. If the claim is about galaxy emptiness, then lensing and dynamics should be consulted to assess mass emptiness. If the claim is about a specific galaxy type, then a matched population study should assess frequency and compare to models. If the claim is about gas, then absorption statistics and ionization modeling should be used. Without this mapping, the claim remains an impression. At this inward stage, the model is expressed as linked expectations that can be tested. The final inward step is to describe what targeted observations and analyses would most decisively discriminate between a normal extreme and a genuine mismatch without speculation, focusing on practical steps. Deeper uniform surveys for low surface brightness, galaxies, neutral hydrogen mapping, multiple background sightlines for absorption, and where feasible gravitational probes. This is the path by which any claimed revelation can be evaluated in the calm, steady language of measurement. The final inward region is the set of next tests that can decide whether what is framed as never expected in the Boötes Void is a genuine mismatch, or a normal outcome sharpened by selection and sparse sampling. These tests are not dramatic. They are practical. They aim to measure the void in traces closer to mass than to light, to improve completeness for the faintest galaxies, and to sample the diffuse gas more densely in absorption. The guiding idea is simple. A void can look empty for many conventional reasons, and an apparent surprise can be created by small numbers. The way to settle claims is to increase the information content of the measurements and to match the measurement pipeline to model predictions. A first decisive test is a uniform deep optical imaging and spectroscopic program designed explicitly for low surface brightness systems in the Boötes region. The goal is not only to detect more galaxies, but to detect them with well-quantified completeness. This requires imaging deep enough that diffuse galaxies are recovered reliably, and requires a pipeline tuned to low contrast objects. It also requires a spectroscopic strategy that can obtain redshifts for faint and diffuse targets, or an alternative distance measurement method that achieves comparable reliability. With such a data set, one can build a volume-limited sample at a fainter luminosity threshold than earlier surveys, and measure whether the void remains as empty in that tracer. If the void fills insignificantly with a population of faint diffuse galaxies, then the earlier dramatic emptiness is largely a tracer selection effect. If the void remains unusually sparse even with deep low surface brightness sensitive data, then the void is extreme in a more robust sense. A second test is neutral hydrogen mapping. Radio surveys can detect gas-rich galaxies that are optically faint. A targeted mapping program can provide a more complete census of gas, bearing halos inside the void, especially low-mass systems. Measuring the neutral hydrogen mass function inside Boötes and comparing it to surrounding regions can test whether void halos host gas reservoirs as expected. It also provides an estimate of baryon content in the form of cold gas. Combined with stellar mass estimates, it yields gas fractions which are sensitive to accretion and feedback. If Boötes galaxies are systematically more gas-rich than predicted, it can indicate that gas retention or accretion in voids is more effective than models assume. If gas-rich systems are rare, it can indicate stronger suppression of baryon capture in low-mass halos. Either result refines galaxy formation modeling and clarifies whether apparent surprises are due to missing faint galaxies or due to genuine halo occupation differences. A third test is absorption sightline densification. The diffuse gas in the void is best probed by absorption against background quasars and bright galaxies. The limitation has always been sightline scarcity. A dedicated program seeks as many suitable background sources as possible behind the void area and obtains high-quality spectra that can detect weak hydrogen absorption and key metal ions. The aim is to measure not one absorber, but an ensemble, the distribution of absorber strengths, and the frequency of metal-enriched systems as a function of impact parameter from the void center. With enough sightlines, one can compare these distributions to predictions from simulations that include ionization modeling. If void core sightlines systematically show stronger absorption than predicted, it implies denser gas or higher neutral fractions than assumed. If they show unexpected metal enrichment, it implies more efficient transport of metals or more internal enrichment sources. If they show weaker absorption than predicted, it implies lower baryon density or higher ionization. The point is not to find a single dramatic line. It is to measure a statistical profile that can be compared robustly. A fourth test is gravitational probing of the mass deficit. For Boötes, weak lensing is difficult but not conceptually out of reach if one uses wide area shear catalogues and careful control of systematics. Even if the signal is too weak for a definitive measurement on its own, it can provide an upper bound or a consistency check on how deep the mass deficit can be. Another gravitational route is to use redshift space distortions around the void boundary, with modern large galaxy samples measuring anisotropy and fitting velocity models. This does not directly give mass density, but it constrains the gravitational potential through dynamics. Together, lensing and dynamics can test the core question: is the void's mass deficit as extreme as the luminous deficit? If the mass deficit is moderate, then the void's dramatic emptiness is primarily a tracer phenomenon. If the mass deficit is unusually deep, the void becomes a stronger cosmological outlier and warrants careful probability assessment. A fifth test is environmental matching for galaxy properties. With a sufficiently complete census, one can select void galaxies and control galaxies outside the void matched in stellar mass and redshift. One can then compare distributions of star formation rate, metallicity, and gas fraction. This tests galaxy formation physics in low-density regimes. It also tests whether the void contains an unexpected population, such as an excess of extremely low metallicity galaxies or an excess of high star formation efficiency systems. Such a result would not automatically challenge cosmology, but it would refine models of how gas cooling, molecular formation and feedback operate in isolation. A sixth test is definition robustness. Applying multiple void finders and multiple tracer thresholds to the same dataset can show which claimed properties are stable. If a surprise appears only under one void definition, it may be an artifact of how boundaries are drawn. If it persists across definitions, it is more robust. This approach can be combined with mock catalogues to ensure that the same definition is used in observation and simulation, All of these tests converge on a calm outcome. They convert a narrative of unexpected revelation into a set of measurable quantities with uncertainties and model match comparisons. In most cases, the result is a refined picture rather than a dramatic overturning. A void like Boötes is expected to exist as part of the distribution of underdense regions. The most likely place for meaningful improvement is in the modelling of how galaxies populate low-mass halos in void environments and how gas is ionized and enriched there. The void remains valuable precisely because it is extreme. It stresses the mapping from mass to light and exposes where models rely on assumptions that may be tuned to denser regions. After these 15 sections, the wind down follows, keeping the same steady tone and staying with what is known and what can be measured, letting the scale of the void settle without pushing toward conclusions.